I'm Yelo from the Computational Science Division in Argonne. So my background is condensed matter theory. So that means simulation since we are in a computing division. So I work on first principle simulations, including like density functional theory simulations. And also my focus is quantum Monte Carlo, mostly in real space. So since we are talking about computing, actually I put a lot of effort on the computer science side. I work on programming models like OpenMP, so we do CPU threading, GPU offloading, and I actually work on the like LVM OpenMP offload runtime, just to do optimization to deliver the best performance for applications. So I also work on a lot of algorithms, try to leverage the best accelerators. So if you have questions in those areas, feel free to have a conversation with me. And also, I do a lot of designing of the applications. But today I will focus on my main focus for ECP, that is to make these material science, material simulation working on exascale computers. It's a many-year effort to reach the final product. So this is the basic outline. I will first give you a quick intro of the quantum Monte Carlo method. I will cover a bit how we completely redesign the application, how the parallelism is done in the code to maximize performance for all the platforms, including CPU and GPUs, although the focus will be GPUs. There's also algorithmic advances we made in the code to leverage the best operation you can do on GPUs. That is the gem. Everyone knows about it, I assume, hopefully. So we try to maximize the performance, and we'll also showcase a bit of the performance as a result. So just quick acknowledgement. So this work is supported by the Exascale computing project, the application development part. We have a team of people working on the code, including the whole code design, maintenance, testing, infrastructure, like doing all the testing, deployment, so a lot of people. So let's start with the basic spectrum of electronic structure methods. So from the left to the right, on the left, you have the most accurate. Also, you can, if you have infinite resource, you can hit the exact solution, that is the CI, but the computational cost is exponential, exponentially grows with the system size. On the rightmost side, you can do chip type binding type of methods. It's not really fully ab initio. So between most people use actually in the field is the density functional theory. It's actually a very good tool for studying a lot of materials, actually give you qualitatively correct results. I'm working on a slightly more advanced many-body method, which is called quantum Monte Carlo. So this method, one advantage is it actually have very good scaling, especially suitable for the supercomputers we have, which consists of tens of thousands of compute nodes. So the scalability, although it's very expensive, but due to the good scalability, it's actually very suitable for the supercomputers nowadays. But on the other hand, it's more expensive. That means the system size we were studying was very limited. So these are simulations I did over the years. Because the computational cost usually is associated with the electron counts. You can see, even we use pseudo potentials, the electron counts is limited by the capacity of the computer. So we can roughly only simulate like several hundred, and maximum like several hundred of atoms in a simulation cell. Although that we are aiming at better materials, more complicated materials, yeah, on the leftmost, you see it is a very simple crystal structure. But if you think about adding a defect, removing an atom, injecting a different atom species, or you have interface that have twists, in the boundaries. So those simulations actually do require you to have big simulation cells. So we would like Exascale computer to help us tackling those problems. So we want just by doing all the code side of development with the better hardware, I mean GPUs, very faster GPUs, we want to solve those petascale problems much faster, and also we want to solve much larger problem sizes. So for Exascale computing project, we are aiming like doing 1,000 atoms in a simulation cell and reaching like 10,000 electrons. So give you quick ideas about quantum Monte Carlo. Here's a diffusion Monte Carlo, but I don't know how many of you just did a very quick, like using Monte Carlo to calculating pi. It's just an advanced version of it. So when you are doing calculating pi, you have a Markov chain getting evolved. But if you want more statistics, you can have multiple, this Markov chain happen in parallel. So it's similar in QMC that we call each on the configuration, we call it a worker, it evolves by itself. Then we have a population, just many ensembles. So by just evolving those individual workers randomly, since it's a projection method, you adjust the weights. At the end, you do some low balance. So mostly the calculation pattern will be just massive parallel Monte Carlo simulations. Okay. So now I will talk about how we redesign the overall parallelism in the code to achieve best performance, consider the evolution of hardwares today. So I mostly work on this code called QMC pack. It is a high-performance open source code. We do development on GitHub, and it's freely used. You can contribute and you can use the code. Actually, when I do talks, I actually give a lot of examples and point you to QMC pack website, give you links. We have a very permissive license. You can even just take the code and use it, take the source code and integrate into your own code, which could also save you doing a lot of programming work because it's very modular. So the code itself is C++. It adopts MPI plus X. Long time ago, we know that MPI plus X is plus OpenMP threading or plus CUDA. But over the years, we moved beyond it. In QMC pack, now MPI plus X refers to, we have higher level OpenMP threading. And under it, we have each thread talking to the GPU, either through OpenMP offload or through CUDA HIPSYCL, those vendor-provided programming models. Just to demystify the name of quantum Monte Carlo and also help you understanding how the parallelism is done, you can break the name into two parts. You have quantum, which actually in QMC pack refers to electrons. You are solving Schrödinger equation, so it's electrons. You have many electrons, there's one layer of concurrency, so you can do parallelism. The other part is Monte Carlo. As I've shown you that you have massive Markov chains evolving, so it's very similar to other Monte Carlo codes. So actually, if you have a Monte Carlo code, you can think about whether the pattern used in QMC pack can be leveraged in your code. So Monte Carlo part, we have a lot of workers, a lot of large ensemble. So you can just break them into chunks and send them onto different compute nodes. So there's no challenge, there's a bit challenge, but it's naturally easy process. You just distribute the ensemble, the workers that way. The plot I'm showing here is the study we did, the scaling study we did on Mira and Titan. Mira was deployed here at ALCF. It's actually have so many, I think 500,000 compute nodes, which is higher end of node count nowadays. Actually, it seems to be the past, not even nowadays. The node count actually drops, but we will not have no trouble scaling to this high number of node counts. Then Titan is roughly 4,000, 5,000 node counts, similar to machines nowadays, actually. So the code itself, just by parallelized over Walker, have very good scaling, both weak scaling and strong scaling. So that's not very interesting, I would say. Since the node, beyond node problem, no concern, our focus is within node, the node architecture, how to maximize the performance within a node. But in QMCPAC specifically, we are running at 1 MPI rank per GPU. So the focus is one, how to kind of maximize the performance within the MPI. So, okay, I should fix that, it's 2003. So the current main production machine for us is the Perlmutter machine and the Argonne Polaris machine. They are of the same architecture, have the AMD CPU plus the NVIDIA GPU. Of course, we are working on Frontier. We have allocation on Frontier, so we use it. It's still not fully satisfactory, I would say. Then our Aurora is currently being installed and deployed, and I'm part of the testing effort. So we want to design QMCPAC to be very performant across all those machines. So you don't invent like completely rewrite a code from scratch, right? You have years when you port a code to GPU or report a code to GPU. In the case of QMCPAC, you understand what they do in the past. You learn from the past. So as I explained, in QMCPAC, we call it nowadays legacy CPU implementation, which was the initial implementation. So as I explained, Monte Carlo are evolving. So it's a sequential loop. You cannot parallelize it. It's a time sequence. However, the workers, it can be easily parallelized. So beyond node over MPI, within node over threads. That's very natural. But within a worker, we are further doing random walking by each time move the electron, single electron each time. So it's actually also a sequential loop, which is not a problem for CPU because different threads, yes, they do accept or reject this type of divergence, but once all the electrons of each walk's been moved, all the threads doesn't have load balance issue. It has its limitation. The number of workers cannot be too high because your CPU is just so weak. And number of electrons cannot also be too high. It's weak and the number of core count is limited. So this is not good for GPU. Then about 10, now maybe 12 years ago, we have the first CUDA-based GPU implementation. We call it legacy CUDA implementation in QMCPAC. So the one major change is that the innermost two loops, the single electron move and the worker loop got interchanged. Now within a node, all the workers will move in lockstep. Although yes, you will deal with a bit of the rejection case, but overall, you kind of always bundle all the workers together. And then the benefit is clear. We know that GPU is, if you hand it a big chunk of workload at a time, altogether at a time, it can solve it very quickly. So by leveraging that, this implementation seems working pretty well. Even the code still works today without much modification. The downside of this is clear. The number of workers can go very high, but the number of electrons is limited simply because GPUs in the old days still not perfect in today. GPUs is kind of structured with fine level tiles, individual, you call it, in NVIDIA's code SMs. So the compute power of each SM, which kind of gauge the per worker performance. So it cannot go too large systems. But as I explained, we want to hit a large electron count by changing it. So if you look at the GPU code in old GPU implementation, you clearly see there's only one thread doing the work, or maybe there's no thread, and there's only one process doing the work. So as the GPU gets much faster nowadays, the GPU solve part becomes so small, but the CPU preparation just kills all the time. So we would like to change this scenario by introducing a unified kind of framework to handle the workers. We call it batched drivers, which cover a better spectrum in the number of workers and also number of electrons. So this is our solution by forging these two code paths. Actually, there are even worse scenarios. The legacy CPU, legacy GPU in QMC-PAC is totally incompatible, but we would like to fix that situation. So now the new design was within an MPI rank, within a single MPI rank, the populations are subdivided into crowds. So beyond crowds is still independent. Within crowd, all the workers are still doing lockstep. By doing that, we kind of have the best side of both CPU scenarios and GPU scenarios. So if you just set the number of the size, cross size to 1, you decay to the perfect, we are happy with the CPU implementation. But if you push, there's only one crowd, you have the GPU behavior. But our goal is to have something in between that is flexible and switchable and maximize the performance for us. So a bit more about GPU porting in QMC-PAC. What we did was to use the mostly OpenMP target feature to offload to GPUs. It seems working pretty well for QMC-PAC. We had a long time kind of questioning whether the compiler runtime has been matured. And recent, I think 1 year, most of the bugs I hit, I blame the compiler, end up just my problem. So I would say it seems very robust nowadays on NVIDIA, AMD, and Intel GPUs. And one advantage is you can offload to CPUs. So also for a single GPU, even from a vendor, there are multiple compiler choices. You can compare between compilers and figure out what's actually the portable way of doing things. And in QMC-PAC, as I explained, we have those crowds. We still leverage CPU threads, which is also managed by OpenMP threading. So the goal is clear. When we have one thread doing compute transfer, the other thread could also hit the GPU with compute transfer. That is the optimization done by the OpenMP runtime overlapping your transfer and compute. So you get those benefits for free. On the other side, the QMC algorithm doing a lot of matrices, so it's still heavily rely on the linear algebra library provided by the vendors. So okay, so actually we've done the porting of NVIDIA, AMD. Intel is mostly ported in the sense of the features mainly used. There's a bit of less used features not being fully ported, but overall, yeah, we have the library portion also connected. Since we're using the vendor libraries, we also integrate the programming model from the vendor. So overall, that's the QMC-PAC, using both OpenMP to maximize the portability, use the vendor library to maximize the efficiency of those devices, and we try to get the best part of both sides in QMC-PAC. So just to show you, with the crowd design, you get overlap, multiple threads talk to the same GPU dedicated to the MPI rank. You get kernel overlap. If the kernel is not so large, you get compute and transfer overlap, all done by the OpenMP. And this is the final result by switching to this crowd design, this portable design. That is, you have fixed. Think about if you have a fixed number of workers in the old code. which is the red curve. There's only one thread. So the overhead with one thread talking to the GPU clearly is lower than have many threads talking to the GPU, because the GPU runtime, of course, have to do some mutex and kind of make sure it's functionally correct. So at low worker counts, the new design does hurt your performance by introducing more overhead, but as you hit into the larger worker counts, then multiple threads fully leash the potential of GPU. So all the threads just constantly keep the GPU busy and the throughput was maximized. Okay. So apart from just porting the existing code to the new to the GPU, we actually revisit the algorithms because we did some study, see the computational pattern. So overall, if you work on paper pencil, so you figure out the computational cost is n cubed plus n squared. The n cubed part has a smaller prefactor, but n squared part is larger prefactor. So for simulations of small systems, the n squared part is the big portion, and you have to put quite a few kernels. But once you go for the large atom counts, electron counts, actually the n squared part dominates. So we think whether we can improve the algorithm to maximize the performance. The n cubed part, if you've done it poorly, that is using the rank 1 update. It's a matrix inverse, and you don't do inversion all the time. You try to update it in a matrix, the inverse matrix. So if you do it naively, you will see that it goes take up to 95% of your computational cost, which and it heavily rely on BLAST 2 operations, which anyway won't work well on GPUs. So we just revisit the algorithm. I think I will skip this one, basically just to tell you how you can reformulate the matrix using the Sherman-Morrison-Woodbury formula to get the update part into mostly gem calls. And by doing that, we can achieve a very nice speed up on CPU. This is what I obtained. Just think about CPU, which has very low bandwidth, still reasonable compute capability, a CPU core. So I can achieve like 60x speed up on the CPU. On the GPU side, it's more complicated because we still need to manage the data movement between the host and GPU, which is still a severe bottleneck that we can't really get a huge speed up. So the motion's just dragging our feet. So by doing these algorithm changes, we were able to kind of have our new, sorry, not just algorithm change, but just changing the design, changing the algorithm. We can now have a production code in the new design rival the old legacy CUDA code. So if you see the flat line, the black line, which is 1.0, that was our old legacy CUDA code. So the new code is kind of close or beating the CUDA code. This study wasn't done not this year, was 2 years ago. With that compiler at that stage, we clearly inspect the performance of each individual kernels, and we figured out the OpenB kernels at that time was still like at least twice or 3 times takes longer than a CUDA kernel. And we actually work with the compiler developers to further optimize and reduce the generated kernel to reduce register pressure, get those kernels more efficient, eliminate a lot of states in OpenMP runtime in the kernel. So those optimizations further boost the performance. So basically now we have this code have been used in production science on Polaris for more than a year. So we have this design, we realize it on the NVIDIA GPUs with the NVIDIA software stack. We also try to make it working on AMD. So far, AMD is still there's a bit issue in the software under the OpenMP runtime. That is the Rocker runtime, which service both the HIP and OpenMP. It has some bugs, and we figured and still working with the vendors to fix that. And then on Intel's, actually, we just switched the library calls to MKL, and we didn't find any headache. So that was a quite happy experience. So that's what was presented by Intel during ISC, doing comparison with the PVC GPU versus the A100, H100 GPUs. And we are quite happy with the performance gains. I would say it's already kind of big achievement that your first data center GPU is on par with a fully matured product for almost a decade. So just quickly go through some porting challenges I experienced. So again, as I said, we designed the app to have multiple threads talking to the GPU, but it took a while to have the software, OpenMP runtime, and the non-QMC component, non-QMC pack component, all the software beneath to be fully interop and kind of work with each other. So have bug-free, because thread, we thought about like threads. We've been embracing threads for how many, maybe at least 2 decades, but the GPU software developers were offering us something pretty single-threaded still, because they were so heavily tied to the gaming industry, and mostly they're single-threaded. So we just find that having multi-threading was a challenge for all the GPU vendors on their software. So also matrix solver, yeah, we actually hit a lot of the LU factorization and matrix inversion bugs in the vendor linear algebra libraries. Sometimes I even need to implement some multi-trial, like try it once, try it a second time. It may be just self-resolved. They were racing. It's just like we writing GPU kernels for computing. The vendors write libraries. They also have bugs have racing conditions, race conditions in their library implementation. So another challenge is for QMC pack, we really want 2 parts, both OpenMP offload and the vendor library, vendor programming model, having them to work together. So the GPU, the software provided on both sides needs to have a common ground. So otherwise, one challenge was when we work with AMD, a pointer you allocate on HIP side, you say, oh, I want to do a compute on the OpenMP kernel. We just say, I don't know this pointer. What's this piece of memory? I have no idea. So we work with vendors just to have both sides working with each other. So still, I would highly recommend putting our effort doing correctness study, do a lot of tests just to be sure, because there's still high potential of bugs in the compiler and runtime libraries. And for QMC pack, we have a policy that we need to evolve the code as we continuously doing science. So sometimes you can't hit your goal at a single shot. You have to multi-steps and coordinate with other users. Okay, conclusion. So for QMC pack, we put in a new design under the ECP effort, and we were pretty happy with the result that the new code can replace the old design, all the CPU portion and all the GPU portion. Now we have a single one to maintain, and we have much better algorithms in use, and it's ready for exascale machines. So I have the last slide, but I won't present it. So it's just a few pointers if you're curious about doing optimization, like how to program GPU efficiently using OpenMP offload. I did short talk, there's one on YouTube, and also, sorry, it's not SC23, it's SC20. The second one is there's user telecom. You can find slides, and for Intel specific details, you can look at my XPack talk this year. Okay. Sorry.
Thanks, Yi. Are there any questions for him?
So the last portion of your talk is how you're fitting and distributing processing over the supercomputing, correct?
Sorry, could you speak louder?
Basically, I'm wondering if there is a series of mathematical models that you're using, like for fitting. So I'm not even sure how to ask the question, actually. I apologize.
About programming model or?
Yeah.
For.
So you mentioned, for instance, that you found CUDA-like performance on OpenMP, and I was just wondering if you were using identical algorithms or.
Oh, what type of algorithms?
Yeah.
One of the kernel is used in OpenMP is just doing spline interpolation. It's 3D spline interpolation. So we just find the OpenMP offload generate kernel slightly heavier on the register size because there's additional overhead in the OpenMP implementation that your kernel also carries an OpenMP device runtime. So there are things that improving. For example, in OpenMP spec, they introduced the loop construct, which kind of explicitly say, don't do anything OpenMP runtime. There's no fancy thread manipulation on the GPU, that kind of things to catch up the performance with the explicitly programmed CUDA kernel. So there are those differences in different programming models.
Thank you.
Thanks. We have, okay, so one more quick questions, but I suggest if you guys have more questions, just talk to Yi after the talk.
Yeah.
On one of the slides, you flipped up a new implementation performance. One of the slides you showed new implementation performance.
Yeah. So the 1.0 line is the old CUDA, and the green bars are the new code performance.
Okay. Then my question is, you talk about the still problematic and the MD GPU due to Rockbox. The last bullet, the second to the last bullet. So does it mean there is no solution to this at this point?
Oh, actually, I hacked into the runtime because, okay, the quick answer is we have some workaround, but we have to heavily modify, add additional synchronization to avoid breakage of dependency in the GPU runtime. So we do work around it, but we are still encourage a vendor to fix such problems. Because it adds performance penalty on our side, and we cannot maintain it. Yes, we can do heroic runs, but still.